In this particular video, we would like to focus our attention on a very special type of series, a geometric series. So let's begin this video by understanding the definition of geometric series. From the name, it is clear that it is an expression obtained by adding infinitely many terms of the geometric sequence. Remember what is geometric sequence? This is a sequence created using only two numbers a and r, first term and common ratio, right? If you add all the terms of your geometric sequence, resulting expression is called geometric series. Alright, recall the terms of geometric sequence where ar square, ar cube, all the way the general term was ar to the n minus 1 and so on, right? You add all these terms and you get expression called geometric series. Here is a mathematical notation of geometric series. A plus ar square all the way till you add infinitely many terms, or write it in the sigma notation, summation I running from 1 to infinity, a r to the I minus 1. What I am saying is this general term is kind of tricky to compute in sequence itself, and computing nth partial sum is even tedious in form of n. Okay, in case of geometric series, this computation is super simple. I want you to recall the result about nth partial sum of the geometric series. Right, sum of first n terms of the geometric series is really a times 1 minus r to the n over 1 minus r. We learned this formula in geometric sequences. Remember, we have used this formula quite a few times. In fact, in annuity, we wrote down a very special formula from this particular formula. Alright, so again, keep in mind that we don't have to add n terms manually for geometric series. We have a formula to compute sum of first n terms. We only need a, r and number of terms that we are gonna add. Alright, what I mean by that last remark, general remark, is this, that computing sum of first n terms in a general form like this is not that easy for general infinite series. Alright, and that's the reason why we don't use that limit definition anymore. Okay, now here is the genuine question, that how do we know if geometric series converges or diverges? Again, when I say convergent or divergent, it is clear that when can I add infinitely many terms and the result is a finite number, and when can infinite addition result into infinity or negative infinity. Right? So this is the question that we would like to address, and it's a very simple question. We are going to address this using this simple result. It's a straightforward result. A geometric series is convergent if this common ratio sits between -1 and 1. Again, geometric series is convergent if common ratio is between -1 and 1. Alright, and in such case, the infinite sum of your series is going to be a divided by 1 minus r. Okay, again, very simple result. If your series is convergent, you would like to know that what are you going to get if you are adding infinitely many terms, right? So this is the number that you are going to get as a result when your series is convergent. But remember, geometric series converges only when the common ratio is between -1 and 1. Alright, if common ratio is outside this interval, then series is divergent. You add infinitely many terms, result is going to be infinity or negative infinity, or limit does not exist. Alright, so very simple result. I would like to show you a series of examples to demonstrate how to determine if the geometric series is convergent or divergent. I'm going to give you set of problems in terms of both notation, the long notation as well as the sigma notation, right? So let's try to see about 4 or 5 different examples. Okay, so I'm going to start with the first one. Suppose I give you this series 2 plus 1 plus 1 by 2 plus 1 by 4 dot dot dot. All right, you are adding infinitely many terms. All right, remember, we would like to know that if I add this infinitely many terms, will the result be a finite number? If yes, then I would like to know what that number would be. If no, then I need the reason why do you think adding this term result into infinity or negative infinity. Alright, so remember, I need to use that previous result. I need to find out A and R. Based on the value of R, I am going to make a decision that whether or not this series converges or diverges. Remember, to compute A and R, I only need 2 terms of my geometric sequence. This is a geometric series. I know the first and second term of that geometric series. I can calculate A and R right away. Okay, let's calculate A and R. A is 2, R is going to be second term divided by the first term. Alright, so I got first 2 terms. First term is 2, second term is 1. These are the first 2 terms of my geometric series. A is 2, which is the first term itself, and common ratio is the second term over the first term. It's gonna be 1 by 2. Right? I want you to notice that common ratio is between negative 1 and 1, and be sure you write this down because this is a necessary condition for convergence. Right? R value is between negative 1 and 1, so series is convergent. We would like to know where it is heading towards, right? It head towards S equal to A over 1 minus R. We know A, we know R. Throw the values in. 2 over 1 minus 1 by 2. Alright. Subtraction of 1 and 1 by 2 is 1 by 2. You send bottom of the bottom up in the top, and 2 multiplied by 2 is going to be 4. Meaning, if you add infinitely many terms of this form, then the result will be 4. Right? Sum of this infinite terms is going to be 4. Very interesting, no? Let's try another one. Suppose I give you this series. Negative 3 plus 1 by 2 minus 1 by 12 dash dash dash. Again, my goal is to compute A and R. And by looking at R, I am going to decide whether or not my series converges or diverges. Right? So let's compute A and R. My first 2 terms are negative 3 and 1 by 2. A is negative 3. R is 1 by 2 over negative 3. Second term over first term. I get negative 1 by 6. Looks like negative 1 by 6 is the entry sitting between negative 1 and 1. Right? So series is convergent. Where is it heading towards? It head towards A over 1 minus R. So the sum S is going to be A over 1 minus R. It's going to be negative 3 over 1 minus 1 by 6. Simplify this expression in the denominator. I get 5 by 6 in the bottom, 2 in the numerator. Bottom of the bottom, send it into the top. I get 12 over 5. So if you add this infinitely many terms with alternating signs, the result will be 12 over 5. Okay. Alright. Here is the third example. 1 by 3 plus 1 plus 3 dash dash dash. Again, it's clear that I need A and R. I just need to look at the value of R and then decide whether or not the series converges or diverges. Looks like A1 is 1/3, A2 is 1. First term is 1/3, common ratio is 3. Looks like common ratio is outside negative 1 and 1. So I will simply write that R is bigger than 1, so series is divergent. That's the end of the story. You add infinitely many terms, result will be infinity. Okay, so that's again fairly simple deal, no trick, right? value of r immediately tells you whether series converges or diverges. Let's try one problem in sigma notation. Suppose I give you sigma I running from 1 to infinity, 3 to the I plus 1 over 2 to the I. Okay. In order to determine whether this converges or diverges, I need to calculate the first two terms. To calculate first two terms, plug I equal to 1 and I equal to 2 to get first two terms. Plugging I equal to 1 gives me 3 to the power 1 plus 1 over 2 to the 1, which is 3 square over 2. It's gonna be 9 over 2. Plugging I equal to 2 gives me 3 to the 2 plus 1 over 2 to the 1, 2 to the 2, right? Which is going to be 27 over 4. So I got first and second term. I can write down A now. A is the first term itself. Common ratio is the second term divided by the first term. So 24 by 7 divided by 9 by 2, right? If you simplify those entries, you get 3 by 2, all right? 3 by 2 is bigger than 1, yeah? So that means the series is divergent, and that is the end of the story. You add infinitely many terms, result is infinity, right? Let's try one more in terms of sigma notation where series turns out to be convergent. Okay, so I have I running from 1 to infinity, 5 times 3 to the I plus 1 over 2 to the 2i. Okay, once again my goal remains the same. I need A and R. To compute A and R, I will need two terms of the original geometric sequence that I added to form this series, right? How do I get those two terms? Plug I equal to 1 and I equal to 2, and that's pretty much it. Let's do that. So I plug I equal to 1 and I equal to 2. I equal to 1 gives me 5 times 3 to the 1 plus 1 over 2 to the 2 times 1. Seems like 45 over 5 is what we get. And I equal to 2 gives me 5 times 3 to the 2 plus 1 over 2 to the 2 times 2. If you simplify, you get 27 times 5 over 16, which is 135 over 16. A is 45 over 4. R is the ratio of second and first term, 135 over 16 divided by 45 over 4. You can notice the cancellation of 45 from the top and the bottom. All right, left over will be 3. You can cross out 4 from the top and the bottom. Left over will be 4 in the denominator. Okay, I get 3 over 4. Be sure you drop that genuine determinant down, and bottom of the bottom goes up in the top. All right, so 3 over 4 is what I get. Clearly R is between -1 and 1. Series is convergent. All right, it converges to A over 1 minus R. So infinite sum S is going to be A over 1 minus R. Plug the values of both of them. 45 over 4 divided by 1 minus 3 by 4. Okay, 1 minus 3 by 4 is 1 by 4. If you send bottom of the bottom in the top and drop this denominator down, you will immediately notice cancellation of 4 from top and the bottom. Meaning, if you add infinitely many terms in this series, the result is 45. Okay, all right, so these are the 5 examples of checking if geometric series is convergent or divergent. I would like to show you one more cool way to use geometric series. Geometric series can be used to convert infinite repeated decimals into a fraction. All right, so if I ask you what is 1 divided by 4, you would say it's 0.25, right? You can use your calculator. Any fraction can be converted into decimal. All right, some of this fraction, they do not have terminating representation. For example, if I ask you to divide 1 by 3, all right, dividing 1 by 3, if you use your calculator, you will get 0.33333 repeating infinitely many times, right? So this is the representation of fraction as a in terms of repeating decimals. Every fraction has either terminating or repeated decimal. This is something that most of you have seen in your high school, right? As I said, going from fraction to decimal representation or repeating decimal representation is quite simple with the help of calculator. The question is, can we go backward? All right. Answer is yes. With the help of geometric series, we can go backward as well. Okay. Let's try to understand this with a couple of examples to end this story. Okay. So here is the first example, converting repeated decimal to fraction. Suppose I give you this example. You have 0.333 repeated infinitely many times. Many textbooks, they use this bar notation to represent infinite repetition of particular digit or set of digits. Okay, so there is this little bar on the top of 3, meaning 3 repeats infinitely many times. Instead of writing it in that weird way, you can always choose to write it in this way. Okay, what I want you to do here is I want you to break this 0.333 repeated infinitely many times based on the number of digit that repeats. All right, there is a single digit repetition. All right, and I want you to break this expression in terms of that single digit representation as an infinite sum. Okay, this is how I want you to write it down. 0.333 infinitely many times can be seen as 0.3 plus 0.03 plus 0.003. There is a typo here, it should be 0.003 plus 0.0003 and so on so forth. Okay, so again I would like to break this expression based on number of digit repetition. If one digit is repeated, then I'm gonna break it in form of one digit repetition, 0.3 plus 0.03 plus 0.003, so on so forth, right? What you see on the right side is a geometric series. All right, let's write it down as a fraction. First term is 3 by 10, second term is 3 by 100, third term will be 3 by 1000, and so on so forth, right? It's a geometric series. I would like to know whether it's convergent or divergent. I need A and R. Okay, value of R will tell me whether my series converges or diverges. Looks like A is 3 by 10, R is second term divided by the first term. So 3 over 100 divided by 3 over 10, I end up getting 1 over 10. Looks like the common ratio is between -1 and 1. Series is convergent. Its infinite sum converges to A over 1 minus R. A is known, R is known. Throw the values in. Alright, so series converges. It converges to S, which is A over 1 minus R. 3 over 10 divided by 1 minus 1 over 10. The bottom portion will be 9 over 10. You can cross out 10 from top and the bottom. Left over will be 3 over 9, which is 1 over 3. Remember, this is the example that we discussed earlier too. I already mentioned that 1 over 3 is expressible in terms of infinite repeated decimal representation, which is 0.33333 repeated infinitely many times, right? Okay, let's try one more to end this story. Let's say I give you this example. 1.3 and then 252525 repeats infinitely many times. Okay, again goal is to write down this number in form of fraction. Okay, I want you to notice that this example has two pieces, non-repeating part and then the repeating part. All right, non-repeating part is that 1.3 and repeating part is 0.0252525 infinitely many times, right? I first want you to break the repeating and non-repeating part from each other, because non-repeating part it's very easy to convert it into fraction. Okay. All right, so look at this. I separated that non-repeated part from the repeated part. 1.3 plus 0.0252525. All right, this portion is geometric series. All right, that portion is 13 over 10. Okay, so I am not going to worry about this portion. I know it's fraction form. All right, all I have to do is convert this infinite repeated decimal into fraction. Let's do that. All right, I'm gonna take that on a side. It is clear that we need to convert this into fraction. Let's do that. I need the first two terms only to compute a and r, right? So write down the first two terms of your geometric series, 0.025, 0.00025. A is 25 over 1000. A2, second term is 25 over 100,000. First term is 25 over 1000. Common ratio is 1 over 100. It's clear that common ratio is between -1 and 1. Series is convergent. It converges to a over 1 minus r. A is 25 over 1000. R is 1 over 100. Subtraction of these two numbers is going to be 99 over 100. Send bottom of the bottom in the top and drop that 1000 down in the denominator. Crossing out 100 from top and the bottom, I get 25 over 990. Alright, so 990 is what I get in the denominator. If you want, you can cross out 5 as well from top and the bottom. I'm not crossing it out because I know that I'm gonna add this fraction with something else that has 10 in the denominator. Right, so I just don't want to make the sum complicated. So here is that we are back to the original problem, 1.3252525 infinitely many times, 13 over 10 plus that repeating infinite repeating decimal. I already found a fraction form of that. It was 25 over 990. So 13 over 10 plus 25 over 990 looks like the common denominator is 990. 99 is what's missing under the first term. Multiply 13 by 99. Make the denominator equal and then write it as a common denominator. Get 1287 plus 25 over 990. Alright, if you add the numbers in the top, you get 1312 divided by 990. If you divide these two numbers using your calculator, the result will be this. I want you guys to check it carefully. Right, so that is the end of the story for this geometric series. If you have any question about any of this topic covered in this video, please feel free to send me an email or meet me during my office hour on Zoom. I'll be more than happy to clarify any doubts that you may have. Thank you.